This is the concept of critical points. As we travel along the function, you'll notice that we slow down as we approach the relative maximum and minimum values. In terms of calculus, our derivative is getting smaller and smaller until we approach a derivative of 0. At that point, we have arrived at our critical value. In other words, a critical value is the value of x such that the derivative of the function is equal to 0. These are extremely important in calculus. The critical points gives us information about the function that will prove valuable in application problems. Knowing how to find them is important. Let me show you a quick example. So here's a pretty easy function for f of x, but I think it's a good starting point to talk about critical points. So the first step to find the critical points is to always take the derivative. And in this case, it looks like we got 2x squared plus x minus 1. And then we want to set this equation equal to 0 because we want to find the values that make this derivative equal to 0. So we obviously have to go ahead and factor. It looks like we got 2x minus 1 and x plus 1. And from here, we set both terms equal to 0 using the 0 product property. We get x is equal to 1/2 for one of them, and we get x is equal to -1 for the other. And here we're basically done. These are the critical values. Well, let's go one step further and talk about where the function is increasing and decreasing so that we can identify these as our relative minimums or our relative maximums. So here we have the critical points, and the best way that I like to check whether it's going to be increasing or decreasing is to go ahead and draw a number line. So we have -1 on one side and we have 1/2 in the other. And all we really want to do is we want to test values to the left, in between, and to the right. So for example, I'm going to go ahead and choose a value to the left of -1. That's going to be -2. In between -1 and 1/2, that's just going to be, let's just say 0. And to the right of 1/2, we're just going to go ahead and choose 1. And now what we want to do is plug these values into our derivative. And the reason for that is because the derivative tells us whether the function is increasing or decreasing. So once again, I'm just really going to go ahead and plug in these values into my derivative. And here's the fun part. We don't really care about what the values actually are. We just care whether they're going to be positive or negative. So I always like to go ahead and plug it into the factored form. So for example, in this case, I'm just going to go ahead and start simplifying this. In the first parentheses, I have a -5, and in the second parentheses, I have a -1. Once again, this is pretty simple. We know it's going to be +5, but the fact is that it's going to be a positive value. So I'm going to go ahead and put some plus signs to the left of my number line. I go ahead and do the same thing for 0. Once I plug it in, I have 2 times 0 minus 1 times 0 plus 1. I have a -1 times a +1. So that's going to be negative. Therefore, in between here, I know that my derivative is negative, therefore my function is going to be decreasing. And lastly, let's go ahead and plug in 1. We have 2 times 1 minus 1 times 1 plus 1. That's going to give us a 1 times 2. Doesn't matter what the value is, we just know it's going to be positive. So now we know that to the right of 1/2, the function is increasing. So from here, we can write this in many different ways, but I'm just going to go ahead and say that my function is increasing here. It's decreasing in this interval, and then increasing again. Some teachers are going to start asking for the intervals of increasing and decreasing. So the way you're going to go ahead and do that is say that it's increasing from -infinity to 1/2, union 1 to infinity. And this is a topic of discussion. Do we include 1 and 1/2 in our parameters? I like to think that we don't, but I would love to know your input here. And the function is decreasing from 1/2 to 1. So what's really happening is the derivative tells us whether the function is increasing or decreasing. So it looks like the function increases. It gets to 1/2 at some point, and we have a relative max because it continues to decrease and then comes back up at x is equal to 1. That means that we're going to have a minimum at that point. So just to finish it off, let's go ahead and find what f of 1/2 is going to be. So f of 1/2 is going to be 17/24, and f of 1 is going to be 7/6. That means that we have a relative max of 17/24 at x is equal to 1/2. And we're going to have a relative min of 7/6 at x is equal to 1. And that's how we use our critical points to find the relative minimum, relative maximum, intervals of increasing and decreasing.